Hi, welcome to a very special edition of All Things Aviation and Aerospace. I'm Vince Mickens with the Private Air Media Group. What makes this show extra special is that it is exactly 1 week, almost to the hour, that the Perseverance Mars Rover, a NASA and Jet Propulsion Laboratory mission, will land on the planet Mars. As you can imagine, it is a very busy time for the thousands of engineers, scientists, technicians, and all of the personnel, some even from other countries, that are involved in some aspect of this mission. But before we get started, here's a quick video overview of just a few of the people behind the Perseverance Mars Rover mission. And throughout the show, we will see brief video highlights to give you a better idea of who they are and what they do.
When you go to another planet, there's just so much potential for making brand new discoveries.
I'm actually putting something together that's flying to Mars.
One way or another, you're going to be on the ground in 7 minutes. We want it to be there safely.
My name is Heather Bottom, and I'm helping prepare the spacecraft that will fly our next Mars rover to the Martian surface.
My name is Diana Trujillo, and I work with robotic arms to collect samples on Mars.
I'm Al Chen, and I lead the landing team for Mars 2020.
My name is Michelle Tani-Colizzi.
My name is Mutige Stricker.
My name is Jared Tagdon.
My name is Katie Stack Morgan,
And I'm helping to protect the next Mars rover.
Mars 2020 will be seeking signs of ancient life in the rock record of Mars.
What we're trying to do is to rove around the surface of this unknown planet,
Collect samples
Process the tubes as they come back.
To look for things that we call biosignatures.
so that eventually we can bring those samples back to Earth and determine for the very first time, did life exist on Mars?
But also, where could it be preserved for 4 more billion years for us to find it?
Before the rover actually flies, you have to make sure that everything works properly with the flight software and the hardware.
We hit the atmosphere going, 12, 13,000 miles per hour.
After the journey through space, through the vacuum.
We try to test all of our hardware to the environments that we would see.
So that's where a lot of the testing happens behind me.
we spend lots and lots of hours here testing everything.
It gets put in an oven, it gets put in various chambers and clean rooms.
So what we can see over here is the stacked spacecraft.
The robotic arm is actually right behind me.
This is the place where the magic happens. This is the Mars Yard, and this is where our rovers practice driving over rocky terrain. There are hundreds of people that have to come together and build a spacecraft.
You kind of have to put those different pieces together and make sure that those pieces all are going to work.
And I feel like such a lucky person to be working on this.
Everything that you're touching, all this hard work that you're putting in the long hours.
20 years, your children will be reading this in their science book.
It feels great.
Dr. David Paige, welcome to the show.
Hi.
How are you this morning?
Great.
Good. It's really good to have you here. Very excited to be able to talk to you about a very exciting time right now in space exploration.
Yeah, we're almost at Mars. Basically 1 week out.
Yeah. And, you guys are a little busy right now with everything.
Yeah, I mean, the spacecraft pretty much knows what to do, but we have to get ready down here on the ground, and so that's the main activity.
Yeah. So, well, let me introduce you first. There was a lot that went into setting this, building the spacecraft and putting everything together before you guys sent it out to Mars, or before it started heading to Mars. So there's a lot to unpack with regarding that. So, but let me introduce you officially and welcome you again to the program. So we have Dr. David Paige. Dr. Paige is a professor at UCLA Department of Earth, Planetary and Space Science. He's also the RIMFAX Deputy Principal Investigator. RIMFAX is the acronym for Radar Imager for Mars Subsurface Experiments. So it's going to be interesting to hear about that and other things that the rover will be doing once it lands and that type of thing. But I'd like to step back for a minute and just get an idea from you of your background. How did you get into space exploration, and particularly becoming a professor and teaching it at UCLA? And where'd you start with all of this?
Well, I started like everybody does, going to school and just, going through regular classes. I was always interested in science. I remember I saw some stuff my mother showed me when I was a little kid. I would, draw pictures of volcanoes and dinosaurs and spaceships and, the usual kind of thing. I grew up during the 60s when the, space program was a really, really big deal.
I remember those days. It was very exciting back then.
Yes.
Exciting and inspiring, actually.
Absolutely. And, even when I look back today, like, that, Apollo 11 film that was, came out on the 50th anniversary, it
Yes.
really was a truly amazing time in terms of space exploration. And so, I'd read Life magazine and, get caught up in all the details about the things that were happening. So I was, way into it. But I was also interested in science, and I didn't really know that, there was kind of an intersection between these, two fields in
Sure.
terms of, using space as a tool for science. Usually at the, younger stages, it's more kind of, oh, gee whiz, we're doing this. Isn't that really cool sort of stuff. But gradually I, came to understand that, there's you can get involved in this very much coming at it from the perspective as a scientist that uses what's going on in terms of space exploration as a tool to, gather data. And, nowadays, of course, it's just taken for granted. Of course, yeah, you can do science in space, but, this was sort of the, the very early days of it. And so I sort of realized that this was like a pretty good mix of activities to get involved with the science and do it from a space perspective.
It's really important that we send a rover that's clean and we make sure that it doesn't contaminate Mars. My name is Mutige Stricker and I protect Mars from Earth bacteria. The next Mars rover is slated to go to Mars, collect samples so that eventually we can bring those samples back to Earth and determine for the very first time, did life exist on Mars? There's nothing that we can build that's sterile. So we take swabs and wipes of the spacecraft as it's being built. It gets put in an oven, it gets put in various chambers and clean rooms so that we can maintain that level of cleanliness. If we do find something on Mars, we have to make sure it's something that actually came from Mars and not something that hitched a ride. This is the place where the magic happens. Oh, it's definitely cool. In this lab, we look specifically at spores. So spores are those hardy microorganisms that can actually survive if it made it on the spacecraft in the journey through space, through the vacuum. It's very humbling to be a part of this big project because there are hundreds of people that have to come together and build a spacecraft. There's no one person that can say, I did this, I made this happen. It's always a we. I owe it all to Carl Sagan and watching the cosmos. I remember being a little kid, going to the public library and renting that VHS. And from that moment, the light bulb turned on. It actually was the start of my passion of science communication. We are citizens of our universe. We have to be good ambassadors when we are exploring other planets, other moons. So it's the right thing to do.
So one of the things that I wanted to touch on starting out with, and I should also mention that we have a couple other guests that we're going to be on. One, I'm still going to see if she can make it. She's an essential part of the rover itself in terms of when they were building it and that type of thing. And then she's a systems engineer. Her name is Anais. And then there's Dr. Lazio. He's part of the Deep Space Network. He's the chief scientist for them. And I was really looking forward to him, but he literally is in a meeting right now regarding next week. So being 1 week out from this, I was lucky to get you and hopefully maybe Anais during the program. But I do understand that you guys are just a little busy right now. So, but I wanted to start with talking about, and I'm hoping that you can share some things about the construction of the rover when you first got involved with building it, and you can tell us a little bit more about the RIMFAX. And then, of course, it was launched and then tracked, and in a week, it's going to actually land on Mars. So can you give us a little background on that?
Well, these missions that we do in NASA are giant public works projects. In other words, the genesis of these missions starts way back many years ago, where you have strategic plans developed for what we want to do, And, you know, at the very initial stages, there's just a few, you know, analysts, scientists, and engineers who are sort of thinking, okay, what could we possibly do? You know, how much could it cost? You know, what could the goals be? And then gradually over time, you know, the project grows and grows and grows to now, you know, when we're, you know, looking at thousands and thousands of people who are, you know, actually involved with it in a certain way. And, you know, sort of, you know, what happens is the project goes through a set of stages where, you know, it's first very conceptual, and then gradually the details, you know, become more and more clear. And then you get to the point where you're actually, you know, doing the final designs and actually building of the hardware and putting it together and then testing it. And then, of course, the rest of the life cycle is launching it. Right now we're cruising to Mars. Then there'll be a very intensive period when it lands. And then, you know, a period where we're on the surface getting the data. But then there's also a back end to it where even if the, you know, after the mission is over, the data that will be acquired by the, you know, by the mission will be analyzed, you know, potentially for generations and put in the context of everything we know about Mars. So it's really a process that, you know, evolves over a period of decades for each of these missions.
Yeah, speaking of the process and evolution and also the back end, yeah, previous rovers, I take it that you guys, when you worked on that, you took some of what you learned from that and applied it to the new rover along with updated technology.
Yeah, I mean, the technology works, you know, in the same way, you know, it might work for, you know, airplanes. You know, a 747 is a little bit like a 707, and it just
Yeah.
sort of, you know,
Good point. I can't argue that one with you at all.
Moves
yeah,
along.
so as technology improves and you're able to make things stronger, smaller, et cetera, and so forth, then you apply it.
And we can be more, you know, ambitious about what we try to accomplish as we, you know, get better technology and more experience under our belts. So yeah, but each mission is a little bit of a stretch, and that's really where the art comes in, is to try to figure out exactly how much more you can try to attempt to accomplish, you know, given your resources, and also you know, how risk figures into the equation as well.
Okay, so can you explain that a little bit more? You say it's more of a stretch. So are you talking about the depth of the experiments that you do, the length of time that the rover will be active, et cetera, things like that?
Absolutely. And, you know, I think the whole point of NASA in a lot of respects is to develop technology. And so if we're just flying the same thing every time, same old thing, same old, you know, that's not the direction we're trying to go. We're trying to always push the envelope and, you know, do things better each time. And that's driven by a lot of factors, including competition, right? Because, you know, essentially there is friendly competition / cooperation going on in the space world right now. We're not the only ones on our way to Mars. The UAE as well as the Chinese are also on their way or at Mars right now already. So, yeah.
Well, yeah, because one of the things I've learned when I was doing research for the show is that there are orbiters right now around Mars. And so the orbiters are part of the project too. Everybody thinks about landing on Mars, and I think there's a certain fascination with that. But there's other pieces of this, the orbiters that help with the communications, relay communications and data and things like that. And as you said, there are other countries that also have their orbiters there and are sending rovers there. And there's some countries that have already done, you know, attempted landing a rover and weren't successful with it, et cetera. So there is that competitive factor, which takes you and I at least back to the 60s when when there was the space race and that type of thing. But I think it's exciting. I think it's an exciting time for the industry. I'm a little biased. I think it's exciting for aviation and aerospace in this day and age, even with a little bit of a setback with COVID-19. But there's so much going on in our industry now, and there's a lot of support for it. There's a lot of competitive factors with it, and there's just a lot of excitement with the technology, et cetera, and so forth. You were talking earlier that there are thousands of people that work on a project like this, which is, obvious to some, but it makes a lot of sense. But one of the things I wanted to kind of touch on are the various disciplines. Yeah, a lot of our audience, they see the obvious, but I want them to know what's not so obvious, but is applicable. So, shifting, and we can talk about both, but shifting to the Deep Space Network, I was looking at, for example, the architecture of the antennas and how they're put together, and how sensitive they are, as big as they are, and all of those type of things. And I would imagine the same thing applies for the different aspects of the rover. For example, the RIMFAX, which is just one piece of it.
Yeah, well, a good analogy to these sort of missions I like to make sometimes is that of a movie. So if you go to the theater, go sit in your house and watch a movie now. And
Once upon a time,
you watch the movie and say, wow, that was just a great movie. And then, they roll the credits, and hopefully they're playing some cool music, so you stick around and you're watching it, right? Or you just want to sort of hang on to the feeling you had during the movie, and you watch those credits, and then you start to see all these names come up. And you say, oh my God, look at all this. And you start looking at the names, and there's, people all over the world who are involved in doing all these sort of things. In fact, things you had no idea even needed to be done. There's credits for all these people. And you think of the budgets too. Like a big budget movie, might be $100 million or something like that these days.
Right.
It's not like they took that $100 million and, I don't know, blew it on a party, right? They paid all those people to do all that work. And it's exactly the same with these space missions. People talk about the cost. Oh, you spent $1 billion or something like that on the space mission. Well, it's not like we, took a whole, big container of cash and blew it off into space, right?
Right.
Every single, almost every single dollar went into paying people whose jobs it was to work on this.
Sure.
And
yeah, no, I think that's a great analogy. The movie business, right. And especially for all the space fans, if you watch a Star Wars or something like that, if you watch a movie that used a lot of effects and technology and all of that, those credits roll for a good 10 minutes after the movie, right, because there were so many people involved.
Yeah, and there are a lot of analogies here in that, in a sense, if you think about how the movie industry is structured, you start out with the producer, who literally is involved with trying to, just do everything necessary to actually produce the movie. Then you have, directors, you have cast, and you'll see some of those people, on TV in association, with the, with the rover mission, but they are supported by an incredible pyramid of people who are doing basically everything you could imagine needing to be done. And in some cases, it's the same sort of thing where, for instance, you might, if you're working on Hollywood, you might be working on 4 or 5 different movies because you're a specialist in a particular area. Like, let's say you do sound editing, for instance, you do sound editing for this one movie, sound editing for this other movie. And so you're involved in a lot of different projects, and you're being retained basically part-time to work on a lot of things. And so in a sense, what you have is a bunch of specialists who are being coordinated by a management team to then produce the product. And that's exactly what we have going on, in these NASA missions. And it's not, and just as with these movies, not everybody's working for the same company. I don't work for NASA, for instance. I work for the University of California. I have a full-time job as a professor. I teach classes. But then for my research, I then collaborate with colleagues, for instance, in Norway who built RIMFAX, and also, with JPL and NASA who are involved in flying this particular mission.
How often do you get to say you work next to a robotic system that's going to Mars, right? There's not many places in the world that you can do this. My name is Eric Aguilar, and I'm working on a robotic system that will be collecting Martian rock samples so they can be studied on Earth. This is our Hexapod Testbed. It's basically a rover body that allows us to attach, a robotic arm, the adaptive caching assembly, the drill. So that's where a lot of the testing happens behind me. The sample caching system will use a robotic arm and drill to actually take samples out of the ground. And we're looking for evidence of life that may have existed on Mars. The smaller arm that lives inside the belly of the rover and is used to actually process the tubes as they come back with a sample inside. We'll measure it, take some pictures of it, and get it sealed and stored for a future mission to pick them up. You see the robotic arm stretched out, and we have a bunch of engineers and technicians working on installing a model of our drill. Working in aerospace, that was always a passion of mine. What really draws me towards it is the engineering of it. Always working on something new and something that's never been done before. Finding those problems, getting them fixed is really something that I enjoy. In 20 years, your children will be reading this in their science book, and kind of cherish that.
Speaking of teaching at UCLA, what type of classes do you teach in terms of planetary space science?
Right. Well, at UCLA, we have, of course, a Department of Earth, Planetary, and Space Sciences, and this includes everything from the center of the Earth to the surface of the Earth. We have another department called Oceanic and Atmospheric Sciences that sort of handles the atmosphere and ocean. But then once we get out into space again in the solar system, then we take over again. And then there's also a Department of Physics and Astronomy that sort of looks, beyond the solar system. So I teach courses that, sort of deal with the Earth, its oceans and atmosphere, climate, energy. I deal with courses involving the planets, and I also deal with courses involving, remote sensing and techniques involving with, using, spacecraft instrumentation to study the planets. So I teach a wide range of things, and I really like that because that's one of the real benefits of, being involved as in an academic situation is that you grow over time. I sort of, people talk about what grade they're in, and, you might be in 12th grade or something like that. I've been in school my entire life. So, I might be in 50th grade at some level. So I think about myself. I have to learn to stay on top of my job. And that's a real benefit of getting involved in this type of activity.
Yeah, that's true. I translating it a little bit on the aviation side, it's the same thing as a pilot. You're constantly learning. You're always learning the newest technology, and procedures get updated, and now we use satellite a lot more with ADS-B and things like that. So it is definitely something that you continue to learn. So one of the big questions that a lot of the young people watching this program are always asking is, and so I'm asking in two realms. What do you recommend to young people when they're interested in space exploration? They're still trying to fill out what aspect of it, and whether they're interested in the human exploration side or the unmanned, I should say, exploration side, and that type of thing. So with your students and with all your years of teaching, what are some of the things that you can suggest to the young audience out there?
Well, this field is basically a subset of what's generally considered to be STEM. In other words, courses, right. The whole training involved with, mathematics and science are absolutely key. And, when we're looking at students who want to get involved with this stuff, we're going to look at their background in these particular areas. And so, the main advice is to definitely keep up as best you can in these absolutely key courses, and do your best to challenge yourself within whatever opportunities might be available to you, and do as well as you can in these classes. And when I was going to school, I quickly realized that, hey, I've really got to study this stuff and do well in these courses if I'm going to be successful in this particular area, right? Because only a small fraction of the students that start out down this path are able to sort of make it through to the end. The other key thing is to do whatever you can to try to get some involvement outside of the classroom in these particular areas. I was very lucky. I went to a high school where there was a lot of opportunities to do this, and I was able to sort of get my feet wet, in the fields of astronomy and other things like that, during my high school eras. And it was good on two accounts. One, of course, it just gave me some experience and confidence, but also I got to hang out with a lot of other like-minded students who are also going to high school. And this was very important, for my development, because I could see, I sort of see, these are kind of my people. I've sort of recognized that. And, part of, just growing up is sort of learning who you actually are.
Right.
and discovering,
and figure out where to apply it.
and then, figure out where to apply it. But also the demonstrating that you are really interested and committed to working in this is a key part of being successful in this area, because these days we get lots and lots of applications, and we're looking for students that really sort of stand out in terms of distinguishing themselves, in terms of having made the extra effort to get involved and work hard on something. And so definitely do extracurricular activities if you're able to, that are relevant to this field, because that will help you decide if it's right for you, and also give you a leg up in terms of experience.
Wow, yeah, that's great advice. With the young people that are in that process, they're trying to figure it out, or maybe they're excuse me, currently in school, they're in college, and they're studying aviation or some aspect of aerospace, or maybe even engineering, but they're not sure which way they want to go. So my question to you: how did you decide to deal more on the unmanned side versus on the manned side, if I'm saying that correctly?
Well, I mean, from a science perspective, the unmanned really rules. All right.
Okay.
The issue
so
is
it's all about
that,
the science.
Yeah. The issue is that it's very fun and inspiring to go into space. I've never done it, obviously, but only a very small number of people get to do it. And then we're designed to live here on Earth, frankly. That's our environment, and taking it with us and doing that in a reliable enough way that it would be safe to do is a really big chore. And so from the perspective of exploring, just going places that we've never been before, it's really going to be the robots that are going to lead the way. And so my interest is in that. I think it's an interesting distinction between human and robotic exploration. I see myself as actually being an explorer, even though I'm not putting my life on the line right now to go to Mars. Okay.
No,
in other words,
it makes sense, because you are exploring through the technology.
Yeah, we are building technology that lets us explore these places. And, I feel every much of the excitement as anyone would feel if they were going to be dropped down on the surface of Mars and go exploring, except we're doing it again, through this rover that, we've designed to give us the capability to do that. I mean, it does have, the senses, the ears and eyes. It can move around. It can do stuff, maybe not quite as fast or as well as a human could, but still it's going to give us access to these areas, and we are doing it. You know, people are doing it. It's not like robots are exploring space.
Yeah, so I was really looking forward to having Dr. Joseph Lazio, the Chief Scientist of Interplanetary Network Directorate for the Deep Space Network, because the Deep Space Network plays a big role in exactly what you're saying. In order for you guys to get the science and to communicate that back and forth between the rover and here on Earth. Can you tell us a little bit from your perspective about how you do that? So the current Perseverance rover is on its way. It's going to be landing pretty soon, next week, actually, at 3:55 p.m. Eastern next Thursday, and it has a lot of things on it. It has a little helicopter. It has the RIMFAX. It has all these different things for probing Mars and getting samples, et cetera, and so forth. From your perspective, in terms of radar imaging with RIMFAX, which is a major thing that you're involved with, can you tell us a little bit more about how that works and that aspect of this mission?
Let me just go back to just one other point you made, because I think there's an important point to be made there. You know, these trips to Mars are really, you know, expeditions. And, you know, if you wanted to mount an expedition anywhere, like if you wanted to go to the South Pole or you wanted to go to Borneo and stuff like that, it's all based on infrastructure. You need to put in place, you know, a bunch of stuff that lets you do it. Just in the same way, for instance, if you want to do aviation, you need infrastructure, you need the airports, you need, you know, all the support equipment,
air traffic, et cetera.
Yeah, all that stuff is part of it. And so, you know, the Deep Space Network, which does the radio communications, the orbiters, which, you know, relay the data and scope out where the landing sites are, they're all part of this infrastructure. And sort of what we're doing is basically putting infrastructure in place on Mars that enables these types of missions. So while you may think of our rover mission as just one thing, it's just part of a bunch of things that are going on, all of which need to be, you know, choreographed to work and in place. And so a lot of what's done is making sure that that whole infrastructure works. Getting back to your question.
Sure. No, that's a great point. Thanks for bringing that up.
Yeah. What we're doing on Mars with this particular rover, you know, we have a goal, which is to rove around this particular area on Mars, which is Jezero Crater, and search for signs of ancient life, as well as acquire a set of samples that will hopefully eventually be brought back to Earth and analyzed. The rover has a bunch of instruments on it that are designed to work sort of together to be able to scope out what the geology that we're seeing at this particular site is, and then make enough measurements that we can then determine which of the, you know, many possibilities of things that we might be able to sample on the surface might be good. And in a sense, it's very much like, you know, the Apollo astronauts did. They were plopped down at a particular site, and they would look around and say, well, this rock's different from that rock. Let's throw that in the bag. We'll bring it back and we'll take a look at it. The types of techniques that we have are sort of mostly in the category of remote sensing of different types, meaning that what we're trying to do, like in the way our eyes work, you know, the sun hits something, the photons bounce off, and then you know, derive data from that. A lot of our instruments sort of work that way on various scales. Of course, the rover has lots of cameras, lots and lots of cameras for various purposes. Ones that'll take beautiful color images, ones that'll take close-up images, or ones that'll help the rover navigate. We've got a meteorology station. We also have, you know, an arm that has instruments that can, you know, be put on the surface. We've got lasers that can zap things and learn about the composition. What RIMFAX is a ground penetrating radar. This is a new type of instrument to be sent to Mars. These type of radars are used, you know, fairly commonly in the fields of geology and archaeology. And what they do is they basically, instead of sending a radar beam, you know, out around, for instance, to look for aircraft or weather, they would send a radar beam down into the surface and have it penetrate. And what it basically produces is a series of echoes. And those echoes can be used to basically determine the structure of the subsurface. And what happens is the rover will rove along the surface over the terrain, and then RIMFAX will basically make a ribbon of information down below the rover that will inform us as to the structure of the subsurface and help us better understand the context of the geology that we're seeing.
Wow, talk about timing. It looks like Anais just joined us. Anais, you want to bring your video up and audio? It's so great that you could be with us today. I tell you what, while she's doing that, I'm going to show one of the things I wanted to do through this program is show some of the people that are involved in the project. So I'm going to share a screen real quick and show another video.
One way or another, you're going to be on the ground in 7 minutes. We want it to be there safely. I'm Al Chen, and I lead the landing team for Mars 2020. Entry descent landing is all about getting the vehicle from the top of the atmosphere down to the bottom safely. We hit the atmosphere going 12, 13,000 miles per hour. We have to deploy a supersonic parachute. And that's all before we get down into powered flight. So we have a new system that'll take over at this point. It'll start taking images of the ground. That'll let us figure out where we are in latitude and longitude. Jezero Crater, the site we're going to with Mars 2020, was actually rejected for curiosity because the site was considered too unsafe. And really the terrain was way too rough. But now we have the ability to land at these places that we never really could go to before. The Jezero Crater site, if you look at it from space, is pretty obviously a delta. We think that Mars was habitable about 4 billion years ago. So the question is not just where was that life, but also where could it be preserved for 4 more billion years for us to find it later. I worked on Curiosity for 10 years, so this is a very familiar feeling. I think I was too young the first time to really realize what was at stake.
Seeing G's on the order of 11, 12 Earth G's. We are in powered flight.
I've been on the other side of this too. My wife was front and center on Insight. This is actually the same seat that my wife was sitting in for the Insight landing. The same seat that I was in actually back in 2012 for the Curiosity landing as well. A lot of history for us in this room.
Shaft confirmed. Proceed.
We might be uniquely positioned as two folks who are married to each other to know what it's like to land things on Mars.
Anais, welcome.
Hello.
Can you hear me okay?
What is that?
Oh, can you hear us okay?
Yeah, I can hear you okay. Can you hear me?
Yes, I sure can. Am I pronouncing your first name correct?
Anais, yeah.
Anais.
Yeah.
Okay, and how do you say your last name?
Zarifian. I'm Armenian, so hence the IAN at the end.
Okay, well, welcome.
I'm half Armenian.
Professor Paige, are your audio still up? Yeah.
Yeah.
Oh, there you go. You were waving. I thought, oh, no, we lost the audio. Well, and thank you for joining us, at all. I know you guys are extremely busy. And so it's really great to have you on. We were just talking about some specifics regarding the rover and what it's going to be doing and that type of thing. Have you met Dr. Paige before?
I have not. And it's surprising considering I also went to UCLA.
Right. It's your alma mater.
Yeah. And yeah. I'm pretty sure I worked in the same building because I also worked on UCLA's first CubeSat, Elfin, which is in UCLA geology building. It's on the 2nd floor. So we must have crossed paths somewhere, but I've never met him.
Yeah.
Well, it's great to have you on with us today. I really appreciate you taking the time to join us. And I know how challenging it was to try to, make that all happen. How about we start out, if you tell us a little bit about your background. As you said, you went to UCLA, but how did you get into space exploration and specifically the unmanned stuff, et cetera?
Well, I mean, as a kid, I always loved math and science. Applying to college, I thought I wanted to be a physics major. Then people started questioning me, well, what are you going to do with a physics degree? And I kind of kept going, I don't know, be an engineer, maybe something like that. And so engineering wasn't really something that was all that familiar to me in the beginning. And it wasn't until someone suggested, well, why don't you try engineering, that I thought, okay, this could be something that I could do. Then applied to UCLA as a mechanical engineering major, kind of picking it because it was so broad. And then kind of within my career or my time at UCLA, I found that you know, I don't necessarily like, as a mechanical engineer, designing static things. I like designing and building things that move, that interact with software and electronic hardware. And so that's kind of where the interest in robotics started. And I was interested in space exploration kind of since I can remember, but I didn't think I could get a job or internship at JPL until maybe late career. I thought, you know, this is a dream. I'm probably gonna have to work towards it all my life. And then, you know, applied for an internship at JPL after my sophomore year in college, and was fortunate enough to get it. I worked on MSL then too, actually, in almost the same job that I have now.
Wow. Yeah, that's great.
Yeah, and it was interesting because when I got hired into JPL after graduating in 2016, I didn't necessarily get hired into that same position that I had my internship in. I got hired in the mechanical engineering section for something entirely different, and then kind of made my way back to what I was doing as an intern, but except for 2020 instead of MSL. So that's kind of how I got here. And then I guess an important thing to mention is just sort of after my internship at JPL, I think it's that when it really clicked for me that I could really do this right out of school. So I kind of just at that point was set on doing space exploration and working on robotic spacecraft with my degree. And that's when I joined Alpha and was in my junior year of school.
Yeah. No, I think it's a great point that you're bringing up. And if you don't mind my mentioning, I believe you graduated in 2016.
I did.
So not too long ago. That's really good for our young audience to hear that it wasn't going to take you a lifetime to work in an area that you're interested in.
Right. And that's exactly what I have thought all through undergrad and high school. And then, you know, when someone kind of came along and said, you should apply for this internship, it didn't really even occur to me until then. So I'm glad that they did.
Yeah. Before we talk a little bit more about what you do, Professor Paige, do you have any input about that or additional thoughts about what she just shared with us?
Well, you know, it sounds great. I mean, everybody's life is kind of a series of accidents, right?
Very true.
That starts way back in the process, but yeah, I mean, I think what's so interesting is everybody has a story that's, you know, sort of unique to them, and you know, finding their way. And you know, it's just like everything else. It's not like, you know, this was the only thing, you know, we could be doing. It just happens to be the thing we are doing, you know, and we might be equally happy doing something else, but this is just where things ended up.
Yeah, exactly. So let's dive a little deeper into things. Anais, I'm sorry, I hope I get your name pronounced correct before the show's over. We were just talking about the rover, the Perseverance. And, you know, one of the things I looked at when I was researching prior to the show was that there's an actual twin to that rover that was built that's identical to it, so that you guys can do any kind of adjustments or whatever, or look at a problem on the rover that's almost about to land on Mars. Can you tell us a little bit more about your involvement with that and what that's all about?
Yeah, so the twin rover is one of our test beds. Test bed in general is just, like you said, a copy of the rover hardware that we test on. So, you know, we build all these components, we keep them really clean, we put them together into a rover, that one gets sent to Mars. But in the process of building components, we build multiples of those. And then those copies that stay back on Earth that we don't launch to Mars get built into a rover. And my Zoom background, coincidentally, is actually the Mars yard where the twin live. So right behind me, if you can see that.
Yeah. I can actually see a rover back there.
Yeah. And so I was part of the team that helped build this copy. I'm wondering if I could move. There you go. I was part of the team that helped build this copy. So we took all of these components. We had a duplicate of the rover chassis, the wheels, the remote sensing mast, which is sort of like the head. And essentially, we built another rover. There are some differences between this twin and the real rover. For example, this one is not nuclear powered for obvious reasons. We work very closely with it. We work around it. Another difference is that it doesn't have, we don't communicate with it through radio. Because on Mars, you would have the radios communicate with the orbiters overhead, which would then relay data back to the DSN on Earth.
Right.
But for this rover that we use for testing, which is named Optimism, and I'll explain that later, we have this kind of umbilical cable that comes out the back of it. That's what provides the power. That's how we communicate with it and get the data back to this building that we all sit in with our computers and look at the data. And so once this rover was built, I am also part of the testbed team that's responsible for testing the mobility system, which is how the rover drives. So everything related to how the wheels move from the motor controller all the way down to the actuator. But then higher level behaviors like how does this rover do visual odometry? How does it see this rock and avoid it? Does the path from taking a stereo image, determining hazards, and then choosing the next drive step, how does that work? And does it all work like we expect it to?
Sure.
So that's a quick summary of my job.
I'm actually putting something together that's flying to Mars. My name is Michelle Tommy Colizzi, and I'm helping to protect the next Mars rover. The main objective of this rover is to cache samples. They're drilling core samples, and then they will drop them in specific locations on the surface of Mars in preparation for a sample return mission. So what we can see over here is the stacked spacecraft. My role on Mars 2020 is Assembly, Test, and Launch Operations, which is ATLO, where all of the delivered components of hardware come together and make the spacecraft. In the southwest corner over here, we have our Flight Mars 2020 rover, and we have the entire mobility team installing the rocker bogie mobility system. We try to test all of our hardware to the environments that we would see for launch of the vehicle, for cruise, the journey from Earth to Mars, for the entry into the Mars atmosphere, for landing, as well as the surface of Mars. Every once in a while we come up and take a quick look. With all the craziness, you kind of lose sight of it a little bit. Over the years, it becomes like your non-living child. So you really want to see it do well and perform the best that it can. It reminds you that, hey, everything that you're touching and all this hard work that you're putting in the long hours, if it was easy, everyone would be doing it. We're sending hardware that we built on Earth to another planet to go and do science.
So for the sake of our viewers, Dr. Paige was mentioning earlier, he was talking about RIMFAX. That's one of the elements of the aspects of the rover. And Dr. Paige mentioned the collaboration with someone, I believe said in Norway, just for that one particular piece or unit in the rover. But my question to you, and it's really for the audience, is your team there. The team is kind of multi-level because there's a lot of people that work on different things in different areas that then come to fruition there, and it gets mounted into the rover and that type of thing. Based on the need or what it's supposed to do. With the work that you've been doing on it, how big is that actual team, or what does that team consist of just people there at that part of JPL where you guys work on the rover, test the things you're talking about, et cetera? How many people are involved with that, and what are some of their positions?
So the testbed team is, we have, gained and lost members, not to other jobs, but they've moved on to higher roles at JPL. I want to say there's maybe like 20, 25 of us total, I think.
Are they all engineers, or are they different disciplines?
We are all engineers who work
for the testbed team.
Right. And there are, we all come from different backgrounds. Some of us have a software background, electrical background, or mechanical background. But at my level of what I work on, mostly everyone is an engineer. There are some people who come from, who possibly did something before engineering. and then transitioned to it later in life. But as far as the background needed to do what I do, it is an engineering job.
Gotcha. Okay. And that's what you guys work on. So,
wait, I should say
Go
that,
ahead.
you know, we're users of this test bed. We have a flight spare RIMFAX, which hangs off the back of that. And we have driven the rover around the Mars yard with RIMFAX on. And this helps us tell, for instance, if the rover can, you know, sort of walk and chew gum at the same time, i.e. drive and operate RIMFAX, because we're unusual in that our instrument works while the rover is driving. And so, yeah, we did, I think, some squares or donuts or whatever like that around the Mars yard, and we have those data, and it's very valuable to us because it's our best and most high fidelity picture of what we'll actually get on the surface of Mars. And so we use that, you know, to test our software, to test the interface with the rover. And so it's hugely valuable to us to have this, you know, in preparation for the real thing.
So there's a lot of collaboration between the scientists and the engineers as all this is pulled together.
Yeah, constantly. And I mean, the team that I mentioned of 20, 25 people, like, we might be small and we might be the ones conducting the test, but the data that we get is then used by everyone on the mission who designs every single component to make sure, you know, what they built works like they expect it to. So yeah, the data that I probably produced during one of our tests while we're driving and using RIMFAX probably went to Dr. Paige, and I had no idea about it.
Well, and I'm going to ask
so
some really obvious questions, but I just have to ask. It's taken 7 months for this rover from launch to landing next week on Mars. What kind of things do you guys do in the interim while it's being tracked and it's on its way there, et cetera, and so forth? Are you still studying data? Are you still doing tests or conduct? What do you guys do?
I guess I'll answer that first. My answer is lots of testing. So everything that has to do with what the rover has done so far, so launch, cruise, entry, descent, and landing, that has been extensively tested in nominal cases, off nominal cases, corner cases, anything you can think of. But the surface vehicle, the rover itself, when it lands, is just capable of doing so much that you couldn't possibly test everything that it could do before we launched. And so we continue to test our driving software, like Dr. Paige mentioned, you know, walking and chewing gum at the same time. There is so many things that the rover is doing. It's not just moving its wheels and taking RIMFAX radar soundings into the ground. It's moving its wheels, taking RIMFAX soundings. But as it's moving and trying to decide where to go, it's taking images with its cameras. It's creating a stereo pair, processing that stereo pair, and identifying hazards in front of it. There are just so many things that run in parallel. And the system is just so complex that we continue to test until landing. And then even after landing, if, you know, something goes wrong with the rover, we want to try and recreate it on our test beds and see if we can solve the problem. Or if we want to do something new with the rover, maybe a combination of behaviors or tasks that we haven't tested together, we're going to try it on this test bed before trying it out on Mars. So that is what I have been doing. There are also dress rehearsals for how we're going to operate the spacecraft. When we land,
Right.
It is not the first time that we are sitting there looking at rover data, right? We conduct these operational readiness tests where we pretend that this rover, or maybe another one of our test beds, is the real thing. And we port that data over to all the instrument teams, all of the engineering teams, and they look at it as if it were coming from Mars. And we kind of play pretend. We do this dress rehearsal. If you could think of operations, putting on a play, you have to prep for it. It can't be the first time you're seeing this stuff. So that is what we've been up to.
Sounds like you've been really busy. Dr. Paige?
Yeah,
You're nodding in agreement.
Yeah, what a lot of people don't realize is that a lot of things are done on these missions just in time. In other words, we have a real deadline in terms of launching, the mission, because the opportunities to go to Mars only come like once every 2 years. And so we'll do everything we possibly can to make sure that launch goes okay and then the cruise goes okay. But the whole time we're going to Mars during those 9 months, or 7 months or whatever it is, we are doing all the things we didn't do before we launched it to make sure that it works. And this could include, developing software, training the team, all that kind of thing. It's very fun to contrast how doing a mission to Mars is different from a mission to the moon. I'm also involved in the Lunar Reconnaissance Orbiter. The cruise to the moon took 3 days. And so there was none of this extra time to sit back and to fix everything.
To review everything.
Review and fix and practice everything. It just all of a sudden happened immediately. So it really depends on how things go. And then for outer planet missions, you might be waiting years until you get the data back. So it's very much destination dependent on how the projects are paced.
How does it feel? It feels great. Hi, my name is Heather Bottom, and I'm helping prepare the spacecraft that will fly our next Mars rover to the Martian surface. So here we have the rover test facility for the Mars 2020 project. So the goal of Mars 2020 is to collect samples of the surface of Mars and perform lots of other exciting experiments. There's 7 different instruments on the rover. Some of the work that's being done here right now is integrating the arm and the mast. My role is mostly on the systems engineering of the launch and cruise phases of the mission, is essentially getting it to Mars. As a systems engineer, you kind of have to put those different pieces together and make sure that those pieces all are going to work. You get to kind of see the bigger picture. Before the rover actually flies, you have to make sure that everything works properly with the flight software and the hardware. So I have a really unique story. I actually ended up becoming a professional dancer in New York, and I really lived that out to its fullest and wear all the makeup and rhinestones and things. But for some reason, I always knew I was going to come back to this kind of curiosity that I've always had with space. There's some of that creativity here too. Sometimes I feel like we're kind of like the stagehands in this big production for the rover. It's bringing together a bunch of people, it's making sure that the hardware works, and it's kind of similar to a performance where, on launch day, it'll be the opening night, which is what we're all here for.
So how do you guys communicate the commands to the rover? I know it's through the Deep Space Network, but I guess my question is, how much of it is autonomous that the rover does on its own versus what you tell it to do?
Okay, so yeah, commands are relayed through the Deep Space Network. There are a couple ways that you can communicate with the rover. It has a high gain antenna, which you can use to directly talk to Earth, but also through the Deep Space Network. Or, it has a ultra high frequency UHF antenna that relays data to the orbiters. And I think you can also forward data that way. And so in terms of commanding, I think what your question is how much of the commanding is done explicitly stated, do this stuff versus autonomous behaviors. So because of the light time delay of communication from Earth to Mars, you obviously cannot joystick the thing. You can't say, do this thing, immediately get the data back, okay, do the next thing, because you can't react quickly enough to do that. And so for a certain day on Mars, which we call a sol, we will sequence the commands of the day. So, the rover will wake up and it will have a plan. And, it will go through that sequenced series of commands as we've planned it. But within that sequenced series of commands can be some autonomous behavior. For example, if part of the day's activities are to drive, you would potentially set a goal for the rover some tens of meters away, maybe 30 meters away, say, I want you to go here. And then kind of set some parameters and boundaries of where it can drive and then say, go. And then from there, the rover can actually identify hazards on its own and take it from there. And so those sort of autonomous behaviors can be built in. Other kind of autonomy is what we call fault protection. So if during this long day of sequence command, the rover identifies something in its software or hardware that's gone wrong and it's able to detect it, it can autonomously, detect
Shut
that
down.
Stop not necessarily shut down, depending on what the problem is, it will have different responses. It could go from either just stop whatever you're doing right now and move on to the next thing, or nope, stop, this problem is bad enough. Stop everything you're doing, configure yourself to be in a state, like a safe, stable state, and then wait for the humans to communicate with you again. So that level of autonomy is also really important in keeping the spacecraft safe. And
sure, yeah, in case it sees something that it says this is not right, or it's malfunctioning in some form or fashion. Dr. Paige, does that apply for the RIMFAX aspect of it too? Do you give it a set of commands of what it's going to do and then, wait for it to do that?
Right. And there's a whole process to try to determine what those commands are going to be. I don't just sit at my computer and say, oh, wouldn't it be fun if we did this today? There's a lot of contention for the rover's time and activities. And then there's this whole business about where we decide we want to drive it and stuff like that. And you could imagine, well, you've probably been on a road trip before and, well, maybe we should go here or there. You might have a destination, but there could be a really interesting detour or something you noticed on the way. And when do we stop to get food and what kind of restaurant we go to? All those kind of things are the same thing. And the point is that, it's like a giant bus. We're all on this bus together.
Right.
and we have to somehow work it out. So we get to do, we're there to do and have some fun along the way and learn as much as we can. But, it's a very tough process to try to, work through all these different priorities and do the best we can. There's also a lot of pressure to get as much as we can out of the time we have on Mars. We hope the rover lasts for a long time, but something could go wrong, and so we're under pressure to get the mission accomplished and to achieve mission success. That's the overall goal. So
that's a great point you bring up, and I'll ask you, Anais, how long will the rover be active on the planet, or that you estimate it'll be active?
So we have designed and built the rover per requirement to last, I think, 1 Martian year, which is about 1.5 Martian years. Thank you for the correction. 1.5 Martian years, which is about 2 Earth years. And so that is the minimum amount of time that we expect the rover to, be operational. However, a lot of our rovers have lived far past their requirements. We've been operating Curiosity since 2012, and its requirement was pretty much the same. So
wow, 8 years ago.
We will be operating this rover as long as it can keep going. The science is just too valuable.
Sure. So does the rover recharge itself or something? In other words, is it a lot of it has batteries, but then do they constantly recharge with solar energy?
No, we don't use solar energy.
Let me open the question up. How do you power it for that length of time?
Yeah, so we power it with a nuclear power source. It has a radioisotope thermoelectric generator, or RTG for short. That provides power to the batteries. The batteries charge up, and then as we, drive during the day, or for the use the power from the batteries, and then the RTG recharges them.
Okay.
When we're not doing anything. Well, maybe at all times, but the RTG recharges them.
Yeah, and I open this up to either one of you, maybe you, Dr. Paige, or both of you. How do you determine where you want to land the rover? Who determines that, and is that also a big decision with a lot of people?
I'll talk about the first part. You can talk about the second part. So the first part is, think about a map of the entire planet of Mars. It turns out the land area on Mars, even though it's a smaller planet than the Earth, is larger than the land area of Earth because, only 30% of the land area of Earth is covered by land. The rest is ocean, right? So we have this vast, vast potential area to land. There are some constraints on where the rover can operate, either just because of, temperature, as well as, concerns about maybe, disturbing some sort of sensitive areas due to biology and planetary protection. But, if you have a particular science goal, they're going to be better places than others to study them, right? And so with the Jezero crater landing site, we've picked a place that, has evidence of water in the past on Mars, which is key to searching for evidence of life. And it also has terrain that we can potentially land on, as well as rove around and have access to a variety of rocks. But, there's a certain amount of guessing involved, right? Because you can't really tell for sure what the surface is going to look like once you get down there until you actually do. And so, and the way it worked is there was a bunch of candidate landing sites that were, selected by various science teams. And then ultimately, a decision was made by NASA headquarters as to, which of the many potential landing sites we would go to for this mission, and Jezero was selected. And I'll turn it over to Anais to talk about exactly where the rover lands.
Yeah, I guess I'll zoom out a little bit. I do want to add to the whole landing site selection process that it's not just scientists that were involved. NASA opened it up to a massive, just public forum, essentially. And anyone who wanted to could make their case for a landing site. Anyone, scientist or engineer or not, no matter their background, could come up there, make their case for Jezero because they like the name, for example, maybe no other reason behind it. And so, it's just a huge pool of people who have input into this, but ultimately the decision of NASA. To kind of switch to how we land, or where exactly we land, kind of during EDL. Interesting new feature we have on this rover is terrain relative navigation. So as we come down, the rover can take images, sort of like, if you're looking at a map and you're looking around you and seeing where you are, and then looking down the map to see where you are relative to everything else. That is essentially what the rover is doing on its way down. And by doing that, can identify potential hazards and then divert away from them and land in a safer spot. And that's enabled us to pick a landing site that maybe we wouldn't have been able to with Curiosity, and definitely not before. So we're able to land in more interesting sites, even though they might have potentially more dangerous terrain.
Got you.
But the answer is we don't know where we do not know where the rover is going to land because it might be, we can't say exactly where it's going to be. And so what the rover will do is there's no GPS on Mars, okay? So it will figure out where it is, and then where it is relative to terrain hazards, and then literally divert its course to a place that's known not to have serious landing hazards. And so it's a very interesting process. I saw a movie that showed, where the possible landing sites are. It starts out as kind of an ellipse, and then it gradually turns into little clumps where they say, okay, once it gets this, it might land in this clump of places or that clump of places. We actually have a pool going on the project where there's a map of the landing site, and then all the team members have put a pin in the map. This is all done, electronically, but a pin, and presumably there's some sort of prize for the team member that gets closest to the actual landing site.
Sure. Before we start to wrap up, I wanted to ask you a quick question, Anais, about the helicopter, which is a device that the rover has. I don't know how much you can tell us about it, and what its purpose is.
So the helicopter is a technology demonstration. This is the first rotorcraft essentially that's flown not on Earth. And so the main purpose is to prove that it can be done. And so that's what we're flying with.
So based on the atmosphere, et cetera.
Right, because there's just so much less atmosphere on Mars than there is on Earth.
Okay.
And so, yeah, its purpose is a technology demonstration, but I mean, in proving that you can do that, you unlock so many potential missions and use cases for a helicopter on Mars. You could potentially use it as a scout to scout out different sites before you drive to them.
Exactly.
Yeah, there are so many use cases, and it's going to be a huge accomplishment to be able to do that.
What are you guys looking forward to next Thursday when this, are you nervous? Are you know, what's the feelings about it?
The nerves have definitely set in. Honestly, all I can hope for at this point is a nominal landing. I've just worked so much on this rover and on the surface mission that I would like a safe landing on Mars, and that is all I'm hoping for at this point.
Sure, that makes perfect sense.
I want to hear 2 words: touchdown confirmed. That's what we're all waiting for.
Sure, yeah, everybody will be on pins and needles until those 2 words come out. What I wanted to kind of wrap up 2 things. One that I wanted to ask both of you about. As you're working on this, after it lands on Mars, when do you start working on the next project? In other words, the next rover or whatever. Is that short term, or is that something that you won't deal with for a while you guys are just addressing the current rover that's about to land?
Well,
for this, go ahead. For the scientists, we're always working on the next mission and the next mission after that. There's a whole process of advanced planning, that's involved, and it's sort of a competitive process where different ideas or concepts are, traded off relative to each other. And so, yeah, we're always looking beyond, and that's a real fun part of this whole business, because you get to, it's not quite as serious and as consequential as actually building it. But yeah, we're always working on the next mission.
Yeah, I'll say the same for engineers. So I will go on to do mission operations and help operate the rover while it's on Mars. But at the same time, it's not me. The different set of engineers is always working on the next mission. What are we going to do next? Where are we going to go next? And is it feasible from an engineering standpoint? What would the spacecraft look like? So it's not me, but other engineers are on it. JPL is continuously looking at the next mission.
Sure.
I used to clean houses, and today I'm trying to find out if there's life in another planet. My name is Diana Trujillo, and I work with robotic arms to collect samples on Mars. What we're trying to do is to rover around the surface of this unknown planet to try to find out if at some point there was life on the surface of Mars. On the robotic arm, we have 2 very interesting instruments. The robotic arm is actually right behind me. We will use the arm to place those instruments or the drill that will collect the sample, which are the ones that will be analyzing the terrain and helping us understand what is it composed of and understanding if there was some traceability of life. And I feel like such a lucky person to be working on this. We're standing on the Mars yard. The intent here is to demonstrate that we have enough grip to continue to move the rover up and down in any hill on the surface of Mars. I was born and raised in Colombia. There was a lot of violence going on in my country. So for me, looking up at the sky and looking at the stars was my safe place. I came to the US when I was 17. I learned English, paid myself through college, and eventually applied to be working here. We spend lots and lots of hours here testing everything from how it should be moved, from how we're going to configure it. This is us trying to understand how we will use the hardware and the software to get it to do what we want to do on the surface of Mars. It is more about what your enthusiasm, your passion, and if you're determined to do what you want to do in your life, you will find a way.
So I'm going to ask a question that I actually asked of Dr. Paige earlier, but I'm going to ask both of you again as a kind of a wrap up to what we've been talking about today. And that has to do with career aspirations for aerospace and that type of thing. But I'll put it to the both of you this way. I'm a middle schooler I'm fascinated by aerospace, space exploration, etc. You know, what are the type of things you would recommend as I'm starting to move in that direction? Or I'm in high school and I know I'm interested in it, but I don't know where to start. Or I'm in college and I'm studying aviation and I'm trying to figure out which way to go. Both of you have touched on a little bit, but as we wrap up, I'd just like to get some closing comments from you. Either one.
So for anyone interested in engineering specifically, whether you're in middle school, high school, or in college, and maybe even halfway through college had an epiphany that you want to do engineering instead, my biggest advice is, build something, work on a project, or maybe you don't build something. Maybe you're interested in how something works. Take it apart, put it back together, see what it does and how it ticks. The kinds of things that make you a good engineer, like staying curious, questioning things, and then either designing and putting something together to answer that question, or taking it apart to figure out what's wrong. I mean, that's kind of my job with this rover back here. So yeah, that's probably my biggest advice. Get involved in your school's robotics team, or if you're in college, maybe you have a racing team and you're building cars. Maybe now, I mean, not back when I was in school, but maybe now there are some cool like autonomous drone projects going on. If you're interested in it, build something.
So you, Anais, you are one of 3 people I've met in recent months from JPL, and all of you started in internship programs. So it's clear that the internship is definitely a path to move in the direction you want to go, or to get involved with an organization like NASA's JPL.
Yeah, of course. In addition to, I say, build things and work on things, but all of that really helps you get an internship, apply to internships, get, work experience, and look at that stuff. But I mean, obviously for middle school and high school is not as applicable.
Well, that's a good segue to Dr. Paige, who earlier was saying, do something, get involved in something.
Yeah, and also, take your academic work seriously as well.
Especially math.
Yes, don't get behind in those subjects, because there's a lot of other students who are looking for these opportunities as well, and so our ideal students, the ones we're looking for, are the ones that are combining good academics with a real demonstrated interest and talent, frankly, for this type of work. And so, seek out opportunities. And this won't just be like, put into your lap, okay? You actually have to go out and actively pursue these types of opportunities. And you should, tell people you're interested in trying to find these opportunities. Most of my opportunities came because, I just asked people, hey, what should I do? And they gave me good advice. And so you have to be proactive. It just won't, just come to you automatically. It's something you've got to seek out and actively pursue.
Absolutely. Well, guys, we've run over time, but I wanted to spend a few extra minutes because I was so happy that Anais could join us. Anais is a systems engineer at Jet Propulsion Laboratory and a fairly recent graduate from UCLA. And then Dr. David Paige with the Earth Planetary and Space Sciences. Did I get that right?
Yes.
Say it enough, you can do that. But it's great to have you also to tell us a little bit more about the RIMFAX, the radar imaging portion that you're dealing with. And I really wish you guys and the entire team the best for next week's landing and things in the future with this project and others. But it was great to have you on. I appreciate your taking the time out at a very busy and exciting time to join us.
Yeah,
thank you. It's been a pleasure.
Absolutely. Thank you. So this has been All Things Aviation and Aerospace. I'm Vince Mickens, and we will continue to talk about other opportunities in aerospace at future shows. Everybody take care, be safe, and have a good one. Bye, guys.